Okay, let's go ahead and get started with section 2.3. In this section, we're going to use spreadsheets in order to compute the p-value quantities that we were working with in the previous section. In the previous section, the reference distribution app was used to obtain these p-values. There are certain advantages to using spreadsheets to obtain these quantities, and those advantages will be discussed as we go through these examples. Okay, let's go ahead and get started then with section 2.3. The example that we're going to look at in section 2.3 is the vitamin A case study. In particular, we're going to look at the male data in this example here. The research question was, is there enough statistical evidence to say that WSU males are off target from their daily recommended intake of vitamin A? The observed outcome was that there are 3 of the 14 males were over their daily recommended intake for vitamin A. The reference distribution that we obtained in the previous section is provided underneath simulation number 1 here. The p-value from that reference distribution was 0.0590. We needed to check whether or not that was less than 0.05, which it was not. And the conclusion that we arrived at was that the data does not provide enough support to say that WSU males are off target from their daily recommended intake of vitamin A, with a p-value of 0.059. Now I went ahead and computed a second reference distribution. I used 1,000 repeated outcomes on this simulation as well. The p-value that I obtained from my second simulation was 0.0520. Once again, I need to determine if that value is less than 0.05, which it is not. So I end up at the same conclusion that I had before, that the data does not provide enough evidence to say that males are off target from their daily recommended intake. However, I want you to notice that these p-value quantities are pretty close to that 0.05 threshold. Okay, so even though the reference distribution should provide p-values that are pretty similar, in this case 0.059 is indeed pretty similar to 0.052. But one thing that could happen is that somebody could decide to go ahead and run a third simulation, or a fourth simulation, or maybe even a fifth simulation, in order to try to attempt to get a p-value that's less than 0.05. Remember, if they meet the 0.05 threshold, they have enough evidence for their research question. We don't want people to abuse the fact that slightly different reference distributions produce slightly different p-values. When we use spreadsheets, that problem is prevented. So when spreadsheets are used, you will not get different p-values. Let's talk a little bit about what spreadsheets do then. What spreadsheets do is actually use a binomial probability distribution model. Now, this is a mathematical model, the formula for which is here in the middle of the page. And that formula is, to be honest, pretty ugly. We're not going to have to worry about that. We'll go ahead and let the spreadsheet do all the calculations for us. But this binomial probability distribution is actually just a mathematical model for obtaining these probabilities. Now, this mathematical model is based on an infinite number of repeated simulations, which is nice. We talked about that previously, that a reference distribution that uses more and more and more repeated simulations is better than one that does not. Also, when the mathematical model is used, it will produce a p-value that does not vary from reference distribution to reference distribution. In fact, with a binomial probability distribution, there's just a single reference distribution. And that reference distribution is based on an infinite number of repeated simulations. Talk a little bit about some conditions or assumptions before or for a binomial probability model. Now, these assumptions or conditions should be verified before using this model in a particular example. The examples that we've been looking at so far all meet the conditions of the binomial probability model. Let's go ahead and talk about those now, though. A binomial probability model can be used when there are a fixed number of trials under investigation. So the number of trials that we're going to look at needs to be fixed. That cannot change throughout the investigation or throughout the study. Second, there can only be two possible outcomes. All the examples that we've considered thus far have met that condition. Now, one of those outcomes is usually just generically labeled as a success, and the other is generically labeled as a failure. How about the third condition? The third condition is that the probability of a success must be the same for each trial. And lastly, the outcomes must be independent of one another. What do we mean by independent? What we mean is that one outcome from a particular trial is not influenced in any way by the outcome of another trial. Okay, let's go ahead and put these conditions to a test, I guess, in the context of the example that we've just looked at. So let's discuss whether or not these conditions are reasonable for the vitamin A case study that we looked at up above. In the vitamin A case study, were there a fixed number of trials under investigation? The answer to that is yes. There were 14 males that were included in this study. Were there two outcomes in this study? And there was. A person was either over or under their daily recommended intake for vitamin A. So over or under were my two outcomes. Was the probability of a success the same for each trial? Now in our simulation model, the probability of success was 50-50. Okay, so this example was a 50-50 example. All right, so the probability of being over or under was 50-50 here. So the two outcomes were over under, and the probability of a success there was 50%, and the probability of a failure, which would be under, was also 50%. Okay, and that is when, or excuse me, the simulation model, again, is built under a particular situation. And this is the situation that we built. Our simulation model was under the situation that they were on target. So if they're on target, they have a 50% chance of being over and a 50% chance of being under. Now, are the trials independent of one another? So you have to ask yourself, do the outcomes from one male student influence another male's outcomes? And probably not. What one person eats in this particular study is probably not influenced by what another person eats in this study. So I'm going to say that these outcomes are indeed independent of one another. So it looks like the conditions for the binomial probability model are met then for the vitamin A case study that we considered up above. So let's go ahead and use the binomial probability model to obtain the different probabilities. And we're going to use a spreadsheet to do this. Okay, the first step then is to obtain a list of all the possible outcomes. So we had 14 males in this study. The minimum number that would be over for the vitamin A intake would be 0, and the maximum number that could be over for their vitamin intake would be 14. So I need to create in a spreadsheet just a list of numbers that go from 0 up through 14. Okay. Once we obtain that list, we can use the Binome Dist function in our spreadsheet to obtain these p-values. Now the Binome Dist function can be done in Google Sheets. It can also be done in Excel. These two functions are actually, the function, the Binome Dist function, is the same in both of those spreadsheet packages. So let's go ahead and I'm going to use Google Sheets, and I'm going to go over now and go ahead and set up one of these. And the result that we're going to be looking for is this list of probabilities here. And I will also show you how to obtain a picture of that reference distribution as well inside of Google Sheets. So the instructions here are provided on these couple of pages here. I think it's going to be easier to just go over to Google Sheets and walk through that with you. So let's go ahead and do that now then. So as I've said, I have an empty sheet here, and I'm going to identify column A as the number that we're over. And again, that list has to go from 0, 1, 2, 3, all the way down to 14. Okay, and instead of typing all of those in, I just want to show you how to obtain a list a little bit more quickly, more easily, I guess, inside of Google Sheets. So the first thing, in order to get a list started here, is to go ahead and put the first few digits of your list together. So I have 0, 1, 2 listed here. Okay, I'm going to go ahead and highlight those. So I need to highlight that entire list. I need to grab the icon in the lower right-hand corner of that. So in Google Sheets, you can see that square that's sitting there. I just grab that square, left click, and drag down. And you'll notice that these values will start to be filled in for me. So now you can see 3, 4, 5, and 6 were filled in. Let's go ahead and do that again. Lower right-hand corner, that box that's down there, go ahead and grab that and just drag that down. Now I want to go actually all the way down to 14. Okay, so I need to go down to 14 here. So my list of values need to go from 0 up through 14 here, as is shown. I can edit this if I want to center these numbers, make it look pretty. You can do that if you want, but you certainly don't have to. Now let's go ahead and obtain the binomial probabilities. So let's label that binomial probabilities. Okay, I'm going to use a Binome Dist function, it's called. So whenever I use a function, I need to start with an equal sign. Let's go ahead and make this a little bit bigger so that you can see this more easily. We're going to use Binome Dist. And then there's 4 arguments that we need to provide in the Binome Dist function. The first is the number of successes. Okay, so this is going to be either the 0, 1, 2, 3, all the way down through 14. The second argument is going to be the number of trials. For this particular example, there were 14 trials. The third argument is the Prob Success, it says here. That is simply the probability of a success. Remember, a success here is being over on their daily recommended intake for vitamin A. And that probability is 50%. The last argument here is cumulative. And we are always going to use the cumulative quantity to be set to false. We'll talk a little bit more about that in a minute. So let's go ahead and use the Binome Dist function here in order to compute these probabilities. So I'll go ahead and put in what I need, and then I will explain what those quantities are. Okay, so again, equal Binome Dist. I need the parentheses. I need A2 here. Let's go ahead and type A2 there, because that is where my first, okay, that's where my list starts, I guess is what I should say. The second quantity, 14 here, is the number of trials. So in our study for the males, there were 14 males. The probability of success, okay, or the parameter value, is set to 0.50. All right, this is the quantity that we would use when we're building our simulation model in the reference distribution app. This is the quantity that is provided in the null hypothesis. This is a 50-50 example, so that's why that's 0.50. And then, as I said, we always want that last argument to be set to false. And when you got all that typed in there correctly, okay, let me go ahead and show you what that value is. That value is 0.00006, I guess. So that probability value is pretty small. All right. Now, in order to obtain the binomial probabilities for the remaining, okay, values on my number line, I just need to go back into that cell where I typed in that formula, as you can see here, and I can either drag that down, as we did with our list, so obtaining these different probability values for me now. If we want to look at the formula here in this particular cell, notice that the function reads Binome Dist A7 now. Oops. It's using A7 because I'm computing the probability for having 5 males that are over. So it is when I copy down, okay, so if I come back up here to the first one, remember I typed in A2. But when I copy that down, the spreadsheet is smart enough to go ahead and adjust that from A2 to A3 to A4 to A5 all the way down for me. Okay, so I'm going to want to copy this down for all of my different values on my number line here. So way down here, it should be, what is that, A16 it looks like. My last value in my list is in cell A16, and that's what the formula is using there. And each one of these, it is using the number of trials quantity of 14. The probability of success quantity is 50%. And the cumulative value is set to false on all of these. So these are my various probability values then for all of my different values on my number line. Let's go ahead and show you how to make a graph of those values. Okay, so if I want to obtain a graph of my reference distribution, what I'm going to do is simply highlight the quantities that I want plotted or that I want graphed. I certainly want the number line. Okay, these are going to be the values across the bottom of the number line. And then the heights of each of the bars is going to be determined by these probability quantities. So I need to highlight both of those, both the number line and also their corresponding probability values. I need to go under, I think it's Insert, select Chart. And what is provided here is actually a line chart. Okay, and that certainly has that pyramid shape that we've been talking about over the last couple of chapters. If you want it to look more like the reference distribution apps, from the chart type here, you can simply select the one that has the different bars on it. So if I select the different bars, it'll look very much like the reference distribution app that we've been working with. Notice that the values across the bottom are 0 up through 14, so that's my number line. And then their corresponding binomial probabilities are what's plotted on the y-axis. Let's go ahead and Come back to our spreadsheet here. Slide that plot over a little bit if we want. And now we have the binomial probability values along with the corresponding reference distribution shown here on the screen. Okay, let's go ahead and go back to the notes and pick up where we left off there. So much of the stuff in the notes there are just showing you how to obtain those probabilities and the corresponding graph. All right, let's take care of a couple of questions here on page 29. Does the general pattern in the graph that we obtained from our spreadsheet agree with that from the simulation model? And the answer to that is yes. If we go back up here and look at our reference distribution, remember that the number line went from 0 to 14. The probability of being over is 50-50 when they're on target. So the high point of that graph should be at 7. The expected value would be 14 times the 0.50. Okay, so that's at 7 there. And then the reference distribution should just slide down from that 7. In fact, when it does slide down, there's symmetry there. So if we look at 7, the probability of 7 is at 0.20, 0.21, I guess, if I round. But notice the probability at 6 and at 8 are the same. Probability of 5 and 9 are the same. So these binomial probability distributions have symmetry. In fact, they have exact symmetry when it's a 50-50 case. All right, but even off of 50-50, oftentimes they're very similar to the left and to the right there of the expected quantity. One thing that can happen, and we will see this later on in an example, is that when the probability of success gets really, really small, this reference distribution can get jammed down here on the lower side. And in those situations, you might not have that nice symmetry. Those situations are somewhat rare. Okay, let's go ahead and answer those questions then back here. So does the general pattern in the graph above agree with what we obtained from a simulation model? So yes, the graph is similar. The expected quantity, expected value is 7, and this 7, I guess, is the high point. On our graph. The probability values are similar on both sides of the expected quantity. So again, they have that symmetry there. How about the next question here? The binomial probability value for 5 is 0.1222. So let's go up and check that. Binomial probability for 5 is indeed 0.1222. So what does this value mean in the context of this example? Well, let's go ahead and take off the underlining. There is a 12.22% chance of seeing 5 males that are over their daily recommended intake. For vitamin A, again, this is all for vitamin A. So there's a 12% chance of seeing 5 males that are over their daily recommended intake for vitamin A when males are on target. Okay? So remember, these binomial probability values in our simulation, for that matter, are obtained when the males are on target, or maybe we can say when males are on target, or a 50-50 situation for over-under. Okay, so these probability values are obtained under a certain condition, and that condition here is when they are on target for the amount of vitamin A intake. Now, the math that actually is being done by the spreadsheet is pretty messy. Up above, I showed you what that formula looked like. Okay, and here, the number of trials is 14. So that quantity is n in this expression. The probability that I'm computing up above here is 5. So x is 5 in this expression. Pi, again, represents that parameter value. And that parameter value is set up as a 50-50 scenario. So the pi value that's being plugged in here is 0.5. You can go through all of that math and you get the value of 0.1222 or 12.22%. Again, the spreadsheet is doing all of this calculations for us. And for this course, I'm not going to ask you to do these calculations. We'll just obtain them from the spreadsheet. Okay, let's talk a little bit about how to obtain the p-value then for this particular example. In the last section, we needed values, the p-value, again, uses values as extreme or more extreme than the study outcome. In this case was 3. So from the previous section, we went ahead and looked at the probability values for 3, 2, 1, and 0. Okay, so those values would be as extreme or more extreme on the lower end. And then values as extreme or more extreme on the upper end are going to be 11, 12, 13, and 14. Okay, now remember how we compute that. The expected quantity here is 7. And the study outcome is at 3. So the study outcome is actually, what is that? 7 minus 3. So that the study outcome is actually 4 below the expected. Okay, so I highlight values 3, 2, 1, 0. Then I also need to go 4 above what is expected, which would be 11. So the corresponding value on this distribution is 11. Okay, that's the corresponding value for 3. On the other end of the distribution would be 11. So 11 is as extreme or more extreme than 3, just on the other end of the distribution. So I need to highlight as well the probability values for 11, 12, 13, and 14. These down here are going to be p-value high. These down here on the lower end are going to be p-value low. And I need to add those two p-values up. And the status bar down here in the lower right-hand corner actually will compute that sum for you. So let's go ahead back over into my spreadsheet. I need to highlight values 3, 2, 1, and 0 here. Okay, so those corresponding probability values. And I'm actually using a PC, so I'm going to hold the control button down. I think on a Mac you use the Apple button if I'm not mistaken. And then I need to highlight values 11, 12, 13, and 14. So these values up here are going to be p-value low. These these probabilities down here are going to be p-value high. Down here in the lower right-hand corner, in Google Spreadsheets, and Excel has the same thing, down here on the status bar that's called, it actually computes the sum of everything that I have highlighted. And that p-value is 0.0574. Okay, so that has actually done the calculations for me, so I don't have to worry about doing those. So the p-value quantity then for this problem, using our mathematical model, using the binomial probability distribution, is going to be 0.0574. Now I need to ask myself, is 0.0574 less than 0.05? Which it is not. So I do not have enough evidence for the research question. So let's go ahead and state that. I do not have enough evidence for the research question. Now for the conclusion, which I think you're probably getting pretty comfortable with conclusions by this point. I have my decision, which is the data does not provide enough support. That's the first part. The second part then is my research question. So I just need to come back up here and grab that. And again, my research question was asking whether or not males were off target from their daily recommended intake. So if I put those two pieces together, then the data does not provide enough support to say that males are off target from their daily recommended intake for vitamin A. And then the last part is just to report that p-value as I've shown here. And that's your conclusion. Those three pieces, you provide those three pieces, you have a successfully written conclusion. All right, let's go ahead and do a second example now. We'll go a little bit more quickly through this one. And this one actually has to do with font preference. I don't know if you've thought about this before, but fonts are important when marketing products. Okay. So consideration of what font to use is something that people that do market research need to worry about. In this particular example, they were looking at trying to select a font that was best for selling chocolates. Okay, so we actually have two fonts that are being studied in this example. We have the Signet font, which is shown here. We also have a second font, which is the Salem font. The Signet font is certainly more scripted, more eloquent maybe. And the Salem font has some sharp edges there, not quite as smooth. I think the authors actually suggested that the Signet font was more feminine than the Salem font. I don't know if that's true or not, or what they mean by that, but that was words that they used. Now, the way that they set up this study was that they put two boxes of chocolates, identical boxes of chocolates, on a tray. And they needed to name those boxes of chocolates. Okay, so the two names that they come up with was temptation and indulgence were the two names. Now, half of the people received a tray in which temptation was the Signet font and indulgence was the Salem font. The other half of the people, the temptation brand or name, the temptation name was actually in the Salem font and indulgence was in the Signet font. So they actually changed for half of the people, temptation, the name temptation, the name that was on the box of chocolates in the Signet font. Okay. The name that was in the Signet font was temptation. And then for the other half of the people, they switched it to indulgence. Now, let's consider the questions down below here. In the above pictures, the temptation brand is shown always on the left side of the tray. A statistician might argue that such a setup might introduce bias into the study. Why might that be the case? Okay, so if people are, for example, most people are right-handed, and if this box or this tray is presented in front of us, Maybe right-handed people always tend to pick the object that's on the right side of the tray. It's easier to grab that. You don't have to reach across the tray to grab the other. Okay, so that might introduce bias into your study. And we don't want that bias. It's really simple to alleviate that. You just randomize what you put on the right or left of the tray. That'll take care of that potential bias. Okay, so explain why that might be the case. So let's go ahead and just talk about that real quickly here. Left, right-handedness might adversely or negatively impact the outcomes if one font is always on the left or right side. How about the second question? Well, we already answered that one, I guess. That one's pretty straightforward. How can I alleviate this problem? We simply randomly decide which font to place on the right or left side of the tray. That'd be a simple way to alleviate that potential cause of bias then, is just to randomize which one you put on the left and to the right. Okay, how about this last one? This last one's a little more important than just the potential bias from left-handed or right-handedness. And that is, why did the researchers give half the people temptation with the Signet font, and then the other half of the people the Salem with the Signet, and then the other half of the people got the other name, Indulgence, with the Signet font? Okay, so they did this crossover here, right? They crossed over the names here. Why did they do that? And they did that to prevent confounding from the name. Okay, we want to make sure that they're picking the box of chocolates because of the font and not of the name. So that's why they did that switch there, or that crossover. Okay. So what issues might arise if all participants were presented Temptation brand using the Signet font? So if this is done, so confounding between the name, so confounding between the name and font could happen if everybody received the same tray. So if everybody received one name, so if everybody received this first tray, we couldn't be certain that they're picking Temptation because of the font and not because of the name. But if we mix that up for some people, these people should be picking Temptation because that's the Signet font. These other people should be picking Indulgence because that is the Signet font. We believe that the Signet font is actually better for selling a box of chocolates. Okay, so that crossover that we've talked about here will prevent bias from happening. All right, let's go ahead and complete the analysis then for this particular example. So the research question, is there a difference in the preference of the Signet font and the Salem font? I just wanted to know if it mattered at all. The parameter value here is the probability of selecting a box associated with the Signet font. This is another 50-50 scenario. There's the tray that they were presented. They have two outcomes. They either pick the Signet font or the Salem font. So it's a 50-50 case. They wanted to know, is there a difference up here? So my research question has the words, is there a difference? That's usually a pretty good indication that it's two-tailed here. So if there's 40 people, I guess, did this study, I should have mentioned that. 30 of the 40 people actually picked a Signet font. So the study outcome is at 30 here. My number line goes from 0 up to 40. If everybody picked a Signet font, certainly there would be a preference for Signet font. If nobody picked the Signet font, so what's being tracked here is the number that picked the Signet font. If nobody picked the Signet font, then we'd be way down here, and there would be preference towards the Salem font. In a 50-50 scenario where there is no preference, I should have about 20 people that picked Signet font and 20 people that picked the Salem font. Again, my study outcome was here at 30. So when I'm determining the values as extreme or more extreme than my study outcome, I'm going to need to go ahead and determine what those are. So values as extreme or more extreme than my study outcome. Well, certainly I'm going to have 30 or greater. Okay, so I'm going to need to highlight the probability values for 30, 31, 32, all the way up through 40 there. So those are values that are 30 or greater. Okay. So those are going to be as extreme or more extreme on the right-hand side. And then I need values as extreme or more extreme on the lower end as well, which is going to be 10 or less. So I need 10, 9, 8, all the way down to 0 on the lower end. Let's go ahead and look at that for a minute. So the expected here is at 20, right in the middle of my number line. My study outcome is 10 above the expected. So the corresponding value on the lower end is going to be 10 less than that. So here sits the expected at 20. My study outcome is 10 above. I need to go 10 lower. That's where I'm getting 10 from. So on the lower side, I'm going to use 10 or less. On the upper side, I'm going to use 30 or greater. So again, we have that other side to deal with in these two-tailed examples that we've been looking at. How do I get these binomial probabilities? Again, using my spreadsheet. I'm going to create a column. That column is going to have the number that picked the Signet font. This time that column needs to go from, I'm going to zoom out a little bit here. This time that column needs to go from 0 all the way down to 40. Okay, so I need to create this column A here, needs to go from 0 all the way down to 40. I'm definitely going to want to highlight or start that list, highlight that, and then drag that down. I don't want to have to type in all those numbers. And then I'm going to use the Binome Dist again. My list again starts in cell A2, so that's that first quantity. The number of trials is going to be 40 here. The probability of success is 50% again. This is another 50-50 example. That's the parameter value under the null hypothesis, or how the simulation model is set up. And that last quantity is going to be false. I go ahead and create that binomial probability column. And then I need to highlight, again, the quantity 30, or excuse me, the binomial probabilities for 30, 31, 32, all the way up through 40 here. I'm calling that p-value high, which is when those are highlighted and added up, I get 0.0011. And I also have those corresponding values on the lower side. So I need to highlight 10, 9, 8, 7, all the way down to 0 as well. And because this is a 50-50 example, The p-value low is going to be the same quantity of 0.0011. In the 50-50 examples, there is a shortcut that you can take, and that is to simply, for the two-sided problems, is to simply compute the p-value on the high side and then multiply it by 2. That's a shortcut that is often communicated in textbooks and on other people's PowerPoint slides. One cautionary note, though, that only works on 50-50 examples. If you are different than a 50-50 example, then these two quantities aren't going to be exactly the same. They'll be close. They're not going to be exactly the same. So the two p-values put together are going to be 0.0022, I guess, if I add those together. Okay, so let's finish out this example. P-value here, okay, is the probability of observing an outcome as extreme or more extreme than the observed outcome. Okay, which we said up above, we mean 30 or higher or 10 or less. And that p-value quantity is 0.0022. Let's go ahead and zoom in a little bit now. Zoom in a little bit. There we go. So that p-value quantity is 0.0022. Is 0.0022 less than 0.05? It is. So here I do have enough evidence for my research question. So the data provides enough evidence for the research question here because that p-value quantity is less than 0.05. So there is enough statistical evidence to say that there is a preference between the Signet font and the Salem font in the consumer choice of chocolates with a p-value of 0.0022. Again, writing the conclusion with those three components, the decision, the research question, and the p-value will produce a conclusion that has the necessary parts. Okay, let's talk a little bit about little something extra here. We're actually going to talk about this again in Chapter 4. Let's go ahead and just mention it now because it was mentioned in this article, actually. So one of the things that they say here, let me just go ahead and read this quote that's in this article. One interesting finding is that in both the main experiment and the pretest, we consistently found no interaction of gender with font. In particular, women do not prefer lighter, more scripted, scrolled, or so-called feminine fonts, such as Signet. This equality between sexes certainly makes life easier for the company that would use a font to project its brand in mixed gender markets. Okay, let's talk a little bit about what they mean by no interaction of gender with font. That statement that they're made there is very statistical, I guess. That's a common phrase that we would use as a statistician. So what do we mean by that? Well, the best way to describe that is maybe just through the use of two tables. Okay, now in this study, they did tell us that there were 21 females and 19 males. Okay, so they're pretty balanced across the two genders there. And we also knew that 30 of the 40 people picked the Signet font. So let me just create a couple of tables here, Table A and Table B. In Table A, I had 16 females pick the Signet font and 5 females pick the Salem font. So kind of a 16-5 breakdown there. For the males, we had 14 that picked the Signet font and 5 that picked the Salem font. Again, I need to get up to 19 males here. 16 plus 14 is 30, and that's the 30 individuals that picked the Signet font. Now I'm having to make up numbers in these tables because they didn't actually give me how many females picked the Signet font. They simply said that there was no interaction between gender and font. So these two tables that I've created here are fictitious tables, but they'll go ahead and communicate what we mean by interaction. So in Table A, what proportion of the females picked the Signet font? Well, I would need to take 16 divided by 21. So for females, let's see here, females that picked Signet, it was what? 16 divided by 21, were that the numbers? 16 divided by 21, I'm getting 76% or so. How about males that picked Signet font? There I had 14 divided by 19, so go ahead and do that math, and I'm getting about 74% there. 74% for females, or for males, excuse me. Now let's compute those same probability values or same percentages for Table B. Over here in Table B looks very different here. In Table B, I had all of the females pick the Signet font, 21 of the 21. So that would be 100% of the females picked the Signet font. But not very many of the males picked the Signet font, only 9 of the 19. So again, in this fictitious data here, what would those percentages be? Probably easier to just copy and paste this down here. For females that picked the Signet font, I had 21 out of 21, or 100%. For males, I only had 9 out of the 19. Okay, 9 that picked the Signet font out of the 19. And 9 out of 19 is going to be less than half. Using my calculator here, 47% for that one. So these two tables produce very different outcomes here. We can see that the rate in which the Signet font, the rate in which genders pick the Signet font in Table A are pretty similar. 76% of the females pick the Signet font, whereas 74% of the males pick the Signet font. Those rates are pretty similar here for Table A. But in Table B, 100% of the women pick the Signet font, and only 47% of the males pick the Signet font. So the pattern that I'm seeing in Table B, the pattern that I'm seeing for females is very different than the pattern that I'm seeing for males. In Table B, we would say that the gender is interacting with the font type. So there's interaction that's present in Table B. There's not interaction present in Table A. And what we mean by when we say there's no interaction, we mean that the trend that I'm seeing for females is about the same as the trend that I'm seeing for males. There's no interaction between the gender and their font selection. And that's the situation that they described up above. And that's going to be advantageous because in a mixed gender market, where both males and females are buying the product, they know that the Signet font is going to be the better font here in Table A. In fact, if it was Table B's situation, okay, they would want to use the Signet font for females, but they'd want to switch to the Salem font for males in trying to sell this product. And that's going to prove difficult to use two different packaging depending on whether or not I have a female or male that's buying that package. It's much easier to be in a Table A situation in terms, at least for marketing purposes, or for packaging purposes. It's much easier to have no interaction between gender and the font type. Okay, we'll talk a lot more about those ideas coming up here in chapter 4, I think it'll be. All right, let's go ahead and look at example 2.3.3. And this is once again going to look at the Nebraska parole investigation. So we're going to go back to, I think we looked at this back in section 1.3, so a while back. We picked on, or we were looking at the Native American analysis is the ones that we were looking at. I knew that there were 535 individuals that were paroled. And at the beginning of the study, 6.5% of those were Native American. So I would anticipate that 6.5% of these individuals that were paroled would be Native American as well. So the research question here, is there evidence to suggest that too few Native Americans were paroled against an all things fair situation or no discrimination situation? The null and alternative hypothesis are written here. The parameter value, I guess, maybe I should mention that first, is the probability that a parolee is Native American. So again, there were 535 of them paroled. 6.5% of them should have been Native American under a fair situation. There were 24 Native Americans that were actually paroled. So go back up to our table here. There are 24 actually paroled. And I'm wondering if that was too few. So the research question is wondering if that was too few Native Americans paroled. So this is going to be a one-tailed left analysis. So when I'm talking about which values to be highlighting, I'm going to want to go from 24 on down. So let's maybe go ahead and put that in here. Values as extreme or more extreme will be values 24 and below, or what we're going to want to use in computing our p-value. Go ahead and highlight that. When we're trying to determine as extreme or more extreme, it really depends on, well, it depends on two quantities. It depends on the study outcome, but it also depends on what the research question is asking. Is there evidence to suggest that too few Native Americans are paroled? So that's why I'm going to the left, too few Native Americans. So if there was only 22 Native Americans paroled, that would be even more evidence for discrimination or more evidence for our research question. A lot of people will just talk about shortcuts for this, and they'll say, well, the inequality in the alternative hypothesis points to the left, so that means it's a one-tailed left analysis. I don't really like those shortcuts. I really want you to think about, well, what is the research question, and what values are as extreme or more extreme than the study outcome that support that research question. Okay, and that's going to be the values 24 and below in this particular case. So this is the schematic that we had for our simulation model presented back in section 1.3. That certainly doesn't change here. The parameter value here is at 6.5%. My expected quantity is right around 35 Native Americans should have been paroled. I only saw 24. A number of Native Americans paroled. Okay, that's could go down as low as 0. And it actually could go up as high as 535. Okay, so these numbers in column A need to start at 0 and go all the way down to 535. Using the Binome Dist function here, hopefully we're getting more comfortable with how that works. I have the A2, I have 535 as the number of trials, 0.065 is going to be the probability of a parolee being Native American, and then the quantity false there. Maybe I'll real quickly go over to my Google spreadsheet and just create this for you. Maybe show you a second example so that we're comfortable with computing these things. I'm going to go ahead and just create another one here real quickly. Okay, so as I just said, column A needs to go from, well, this is going to be the number of Native Americans, and that needs to go from 0 up to 535. So let's go ahead and get that list started. And then I need to drag this down all the way down. It's going to take a while. I need to go down to 535 here. Looks like I'm about 300. Now I had a label up there in the first row, and I started with 0. So I knew I had to stop here at row 537 in my spreadsheet. So I need a couple of additional rows at the very top to get started there. So there I stopped at 535. Now I can go ahead and get the binomial probability values here. Binome Dist A2, 535, 0.065, and false. So Binome Dist A2, 535, number of trials, 0.065, going to be my parameter setting here. And then that last quantity is always false there. Now it returned a value of 0 there, and that's actually correct. It's just a very, very small chance that I would not see any Native Americans being paroled. If you look at these, scan down these, the highest probability should be at about 35 or so, because that's the expected quantity. Okay, right around here at 34, 35, you can see that these are getting up to about 6% or so. And these go all the way down to 535. Notice that after, what is it, about 77 or so, after about 75, those probability values are just so small that they zero out. Very, very, very small chance that you're actually going to see that many Native Americans being paroled. Now, when I'm computing my p-value, I need to go, well, my study outcome was at 24, so I need to go 24 and below in order to compute the p-value quantity. 24 and below are what probability values I need to highlight. And when I do that, I'm getting a p-value of 0.0308. It looks like down here in the very corner in my status bar is 0.0308 if I round. Let's go ahead and go back to the notes then. And there I'm showing you what that probability value is there for 24 and below. So there's that 0.038 that I just was showing you. So let's go ahead and make this a little bit larger so that we can see that. Zoom in a little bit. Okay, is 0.0308 less than 0.05? It is indeed less than 0.05. So I do have enough evidence for my research question. So data provides enough evidence for my research question. So the conclusion then there is, be enough statistical evidence to say that too few Native Americans were paroled against an all things fair or no discrimination situation. That p-value quantity is 0.0308. Now, when we're doing this, we need to put this in context a little bit. I've just evaluated whether or not there is discrimination from a statistical perspective. Okay? When we're taking this to trial, we have to do much more than just convince the jury that there's enough statistical evidence that discrimination took place. So this is just one particular bit of information or bit of evidence that would go into a trial. There's lots of other information that they would need to provide as well, but from a statistical perspective, we can say that there were too few Native Americans being paroled. This is just showing you the highlighting of 24 and below. Now, the formal process of using a p-value and comparing this carefully defined probability against the 0.05 rule is commonplace in arguing court cases. So what we've just gone through is what they actually do in a real court case. The outcomes from this formal investigation that we just completed here are similar to those that we obtained back in Section 1.3. If you remember back in Section 1.3, we defined the outlier rule. We determined that the outlier rule was any value that was 25 or less. Actually, when I use my binomial probability model, okay, the 25 remains the cutoff. So when I use the more formal mathematical model for determining a cutoff, 25 is indeed the cutoff value for when I start to believe I'm an outlier. Again, that contains the bottom 5% of the reference distribution. So what we did here with the formalities actually agree with what we did informally back in Section 1.3. All right, before walking away from this example, I want to just look at one more slant on this, or maybe one more alternative analysis that I went ahead and decided to do. And the issue here is, or what I'm concerned about, is that if less and less Native Americans become eligible as the study progresses, okay, so what we did before is we used a 6.5% rate of Native Americans. And those were that was the percentage of Native Americans that were eligible for parole at the beginning of the study. Okay, so the 6.5% is the percentage of Native Americans, the percentage of individuals that were eligible for parole. 6.5% of them were Native Americans. Now, if that rate changes as the study progresses, then that's a problem. Okay, that's going to violate one of our assumptions of using the binomial probability model. The binomial probability model says that the probability of success must be the same for each trial. And if the rate of Native Americans decrease as the study progresses, then that's not going to be the case. That the probability of success would remain the same for each individual trial or each individual person coming up for parole. So here's what I did instead. What I did is just more of a holistic approach. I knew that 902 people were eligible for parole at the beginning of the study. 535 of them received parole. That's about 60%. If I take 535 and divide it by 902, I get 59.3%. So all this is saying is that 59.3% of the people that were up for parole received parole. Now, let me consider the Native Americans. I had 59 people up for parole. Okay. 59.3% of them should have received parole if they were like the other races. So the setup of my the setup of my analysis now takes on the following form. My number line is going to go from 0 up to 59 because I'm just looking at the number of Native Americans. About 60% of the people received parole, or 59.3%. So my expected quantity using this approach is, again, right around 35. Okay. The parameter value, though, is going to be that 59.3%. 59.3% of the people that were eligible for parole received parole. Okay, so this is going to be the setup for this alternative approach here. Now, it turns out that the alternative approach is going to come to the same conclusion as the analysis that we did up above. So how would I set this one up in my spreadsheet? Well, my number line would need to go from, the list of possible outcomes would need now to go from 0 up to 59, not up to 535. My Binome Dist function is going to look as it is here, A2. Again, that's where my list starts. 59, that's the number of Native Americans I have. The 0.593, and that's just saying that, again, 59.3% of the people that were up for parole received parole, and then that last setting would be set to false again. This is, again, the research question is stated as follows. Is there evidence to suggest that Native American inmates received parole at a rate less than the overall parole rate of 59.3%? So what I'm doing here, is just comparing the Native American inmate parole rate to that of the overall rate of that 59.3%. This is, again, one-tailed left. Values as extreme or more extreme are going to be 24, 23, 22, all the way down again. So same as before, 24 and less are values as extreme or more extreme. The probability value I get when I use this alternative analysis or alternative setup here is 0.00297, which I think is going to be 0.0030 if I round. If I do my rounding correctly, that's what that probability value is. Is 0.0030 less than 0.05? It is indeed. So again, I have enough evidence for my research question. So my conclusion, there is enough statistical evidence to say that Native American inmates received parole at a rate less than the overall parole rate of 59.3%. So we ended up coming to the same conclusion as we did before. And this last page is just showing you a screenshot of that binomial probabilities inside of my Google Sheet with that sum down here in the status bar, or that p-value down here in the status bar. So the good news here is that the analysis that I did with that alternative approach matches what I did previously. So using either approach, there appears to be discrimination against Native Americans in paroling in the rate in which they received parole. Okay, I think that does it. We've done 4 examples here where we're using the spreadsheet to compute the probability values. You will be able to do some more examples through the homework assignments. Okay, thank you very much. Until the next video.